So here is a statement in your program, okay? Your compiler is basically going to construct some abstract syntax tree, and then it's going to decorate it and do some analysis and so on. And it has a program representation. In this program representation, you have statements, and each statement is given a unique label S sub I, okay? And we are only looking at statements which fit the polyhedral model, which means that they consist of statements where the left-hand side consists of a write to some array or tensor variable, multidimensional array or a tensor variable, okay? So X is the name of that variable. The index point that is being written to is some function of the loop indices and the program parameters. And that function must be a linear function. Otherwise, this whole machinery goes away. Okay?
Yes, sir.
So that function in this analysis is abstractly being represented as some mathematical function. You will see later on, if you dig deeper into this, that this is really some, it's a linear, multidimensional linear function. It is a mapping from Z to the N to Z to the M, because it is a mapping from the iteration space of this statement to the data space of the variable X. So think of a linear function from an n-dimensional iteration space to an m-dimensional data space. And a linear function, go back, think about linear algebra, it is just a matrix. Okay?
Yes, yeah.
That matrix is what I'm calling F sub I superscript 0, and a compiler can just read the program and construct that matrix. It's like a simple pre-processing that is done before you do any of this analysis. Okay, so the mathematical function is a linear function of the points in the iteration space that map to the points in the data space. And such a function is associated with every reference in the statement, left-hand side as well as right-hand side. The left-hand side function is a write function. The right-hand side functions are read functions, and they may access different data variables. Okay?
So, but what is IN0? I still do not.
Oh, my convention is that so in this statement, there are many references. The superscript indicates which reference in the statement. 0 and then 1, 2, k, all the way up to however many references are there on the right-hand side body of that statement. However complicated it is, the compiler is constructing a representation of that statement, and on the right-hand side, there is some expression involving all other variables that are being read. And I am simply grouping that as some abstract function G that is being computed in the program, the expression body. And it is some function of all the variables that are being read by that right-hand side. So
Right.
yes, there is a little bit of a leap of faith, because I'm assuming that some of the compiler technology that you are just learning has already been absorbed. Sorry about that. Okay. So you have a statement in your program. On the right-hand side is some complicated expression. You're building a parse tree and all that. Okay. And I am assuming that some pre-processing step has taken that parse tree and is simply looking at the references on the right-hand side. The rest of it is sort of turning a blind eye to. Okay?
Yes, sir. And P depends on the inputs to the program?
P depends on the inputs. P is a size parameter, like n, m, etc. I have a matrix that is n by n. And I'm doing, let's think of a simple program that does matrix multiplication. At compile time, I don't know how big my matrix is, right? However, I want to compile it using the polyhedral model for an arbitrary program's input size P, or arbitrary input size. And there may be multiple such size parameters in my program.
Yes, sir.
Okay?
Thank you.
And all of them I am clubbing together as some additional indices. Okay. One of the beautiful things about the polyhedral model is I have this saying that when in doubt, add a dimension. So, parameters, how to handle parameters? Oh, just think of an unbounded set of indices, new indices. There is a lower bound on the size parameter, but there is no upper bound. Who cares? It's just one linear inequality involving P. Okay, the mathematical foundation remains the same. Okay. So please, I think these are very, very good questions, and I'm happy to answer them because I think it is much, much more important to get the big picture ideas resolved rather than know the nitty-gritty details. Those you can always come back to. There are books, there are tutorials, there are lots of other things. So now is the subscript and superscript of my notation clear? Subscript I indicates the reference function came from which statement, SI or SJ, etc. And remember, in my program, there are many statements. I'm just making a list of statement labels. Associated with each reference in each statement, there is a memory access function, F. Okay?
Yes, sir.
If that memory access function happens to be a right reference, then the superscript of that function in my notation is going to be 0. If that reference is associated with the ith statement label, then the subscript of those functions is going to be I. The superscript K doesn't matter, really, because I have all these dot, dot, dots on the right-hand side. Some K. Okay? And basically what I gave you in this math was the set of linear inequalities that resolve this array data flow analysis problem. Okay?
So if that particular K has no dependency on the right side, it'll be a 0, the whole.
If that particular K has no dependence on the right-hand side. For example, if your statement is S equals 0, is that what you're saying?
Yeah, something like that.
Right?
Yeah.
Let's look at this. You're still seeing my PDF, right?
Yes, but without the line. So the last line now is variable domains is domain of statements.
Yeah. Okay, so my statement of, let's say you had a program in which some scalar variable was initialized. There S2. Okay? What is the read access in statement S2? There is no reference in statement S2 because you're assigning a scalar constant. That's actually a wonderful question. Okay? So what I gave in the notation and what I gave to you in this example was was basically how do you solve this problem in the general case? When you implement it in a compiler, of course, certain the special cases, you will have for each reference on the right-hand side of my statement, do an analysis. You will be parsing and you will be traversing the tree of or your compiler will be traversing the tree, the abstract syntax tree of this statement, and you will do some analysis for every reference on the right-hand side of every statement. Well, this statement has no right-hand side reference. It only has a left-hand side reference. And in the left-hand side reference is also very, very trivial because it is taking whatever the surrounding indices are and giving me a unique single memory location because the left-hand side variable S happens to be a scalar. Okay?
Thank you.
Okay. So this was the first big picture problem that we solved. We tried to solve the problem of figuring out precisely what are the dependencies in a program. And it turns out that the true flow, so I have a meeting, like I said, in about 15 minutes. So we want to wrap up in 15 minutes, and then I'm going to let you sleep and chew on this, think about it. whatever you want. Okay, dream about it if you want. Okay. Let me go back and show you.
Sir,
It doesn't make.
sir,
Yes.
can you give some reference about this? Any textbook or anything? So that
This is a wonderful paper by Paul Foutrier, array data flow analysis of array data flow analysis of programs. It was 1989.
Oh, okay, sir, okay, thank you.
Paul Foutrier in 1989. And, you know, Rama will definitely have all the references. Don't worry about that.
Thank you, sir.
Okay. And the paper, believe me, is not an easy read. I promise you that. Okay.
Yeah, that is true, sir.
What I've tried to do is give you the intuition. And the thing is that I chose to present this in a slightly different way. I chose to, you know, so he builds off a previous paper that he wrote, which is on parametric integer programming. And if you read his data flow analysis paper, you at least have to have a good understanding of parametric integer programming. And in my presentation, I bypassed that because I simply said that the lexicographic max of all the points in a program is a piecewise affine function of its parameters. That is the main message from his earlier PIP paper. Okay. And you know, once you have that idea, then there is sort of, it's easier to follow the rest of his paper. Where am I in terms of sharing the screen? What happened? Are you seeing my? Oh, you're not seeing me. You're still seeing my PDF, right?
Yes, sir, yes, sir.
And I have to go and share. I'm going to go back to my PowerPoint. Are you seeing my PowerPoint screen?
Yes, sir.
Okay, good. Now we look at parallelization. So data flow analysis has been done, and you have figured out that you have a program in which at any point in the iteration space, I can tell you what that point depends on as a function of that point, as an affine function of that point. Okay? So I have iteration space to iteration space functions that tell me which iteration depends on which iteration. Memory arrays have all gone out of the picture. Okay? And now we are going to analyze such a program and try and figure out whether there is parallelism, whether you can schedule it in, you know, in a way that exposes this parallelism, and how do you construct a program that implements your desired schedule. Okay? So let's look at our picture. All right. I'm going to ask you these, you know, go back to our simple example. From every point, I have arrows that point to other points it depends on. Okay? So you can think of this as a dependence graph, but you can also think of a mathematical representation of that dependence such that at every point I have some affine function that tells me what is needed to compute that point ij. Okay? If I want to ask you what is the order, because each of these nodes is evaluating one instance of the loop body, right? Let me assume that each execution of one loop body takes 1 unit of time. Okay? There are clearly precedence constraints. You cannot execute an iteration ij before the points on which it depends have been executed. And transitively, those that, points that depends on, and so on, right? So looking at this graph just visually, can you identify an order of execution? Remember, our original order of execution was top to bottom, left to right. And our original execution order took n times m because it executed each instance of a loop body one after the other because it was a sequential program. Our goal is to discover parallelism amongst the dependencies of this program and then to generate a parallel program. How can you detect, or how can you solve this scheduling problem, detecting parallelism? Any thoughts?
In this case,
You can think, you can use any technique that you've seen before, graph theory, whatever, right? So go ahead. In this case,
like you could go diagonally and
you could go diagonally. Can you please try to make that a little slower? Explain what you mean diagonally. Which is the first point that you would execute?
top left.
The top left point. Why is that a legal point to execute?
Because it has no dependencies.
Yes, it is a sink in this graph, right? It's a sink node. There is no outgoing edge coming from it to any other node. We are just repeating the obvious, right? So that is the node that can be executed first. Let us do that and remove that node and all incident edges on it. Okay? Now, can you identify sinks in the residual graph? Are these two nodes the sinks in the residual graph?
Yes.
Very nice. Now let's remove those and the incident nodes on those. So we will consider, again, the residual of the residual graph. And you want to identify what are the sinks in that graph. And they are these. Right? And isn't that what you meant by diagonal by diagonal?
Yes, sir.
Okay. At any point in time along this, everything on a diagonal, any residual graph, all the sinks in that graph can all be executed in parallel. Right? They don't depend on anything. So why not seek to execute all of them in parallel? And in order to do that, one very nice way to visualize what we want to do is to transform this graph such that these diagonal lines become vertical. If the diagonal lines become vertical, that means the horizontal axis can be interpreted as time. I've said a mouthful here, okay? You have to think about this, but look at this. I'd redraw the graph like this, okay? Basically what I'm doing is I'm shifting every row to the right by one more than the previous row, okay? So what used to be a vertical dependence is now going to be towards the northwest. And my diagonals have become vertical lines. Another way of thinking about this is that my new horizontal axis is the time axis, right? I used to have an old set of coordinates ij, but now I have a new set of coordinates in which the horizontal axis is the time. Okay? So That is the key idea of the scheduling problem. You want to find a mapping. This redrawing that I just showed is the key idea of scheduling. Okay? Expose the parallelism, and the kind of parallelism that you want has to be linear or affine function of the indices. Remember those diagonal by diagonal that we talked about? What is the equation that defines a diagonal? I plus j equals constant. That's linear equality. T equals I plus j is a linear function of I and j. My new indices are linear functions of the old indices. Okay? So the second important analysis that polyhedral compilers do, and some might say the most important analysis, is the choice of good linear transformations of the original program. Okay? So I think that's a good point to stop. I sort of introduced this to you because tomorrow I actually don't, like I said, I don't want to go into too many details of how does one choose a good mapping, because that is the subject of very, very intense, a long time of research. It's unreasonable to expect that you get all the details of all that work. I mean, there are very, very smart people who have worked on this for a very long time. Okay. Your takeaway should be that, yes, smart people have worked on it. There may still be open problems. So yes, I can look at it. I can figure out more if that is my interest and if this piques my curiosity. Otherwise, I can also say that, yes, there is machinery to solve it. Let me see how I can use that in building my own compiler. Whatever you are going to do with your compiler, whatever you want to learn, tailor that to what, tailor what you want to investigate based on what you want to learn.